Dear friends, in this video lecture, let us discuss about International Standard Atmosphere. This International Standard Atmosphere being used from the year 1920, but in the beginning, this model had certain defects, so which was developed by US and Europe, and later on this model has been modified, and the data, various in the data has been rectified. So and then further in the year 1952, this model again has been reintroduced by International Civil Aviation Organization. From then, this model is being used worldwide, so, and it is acceptable by the all scientific community. So now let us see the layers in the atmosphere, and then we'll discuss about variation in the properties. When we talk about layers in the atmosphere, mainly consist of 5 layers. So we say so from 0 kilometer to up to 11 kilometer, then it is called troposphere. So this is called troposphere, and so from 11 kilometer up to 20 kilometer, it is called stratosphere. And then above that it is called mesosphere, up to from 20 kilometer up to 50 kilometer. And then above that we have a thermosphere, and above that we have a exosphere. So these are the layers exist in the atmosphere. Generally, our main focus, that means International Standard Atmosphere model, gives the idea and how the data and parameters. So, say for example, pressure, density, and temperature, how they are varying. So that has been described by the International Standard Atmosphere model, and because our main focus will be in the stratosphere and the troposphere, means our main focus will be these two. Here only our civil aircrafts used to fly. So because of this reason, so our main focus will be in troposphere and stratosphere. So the troposphere and stratosphere, here in between the this one, that means at 11 kilometer, this is generally we call it as tropospause. Tropos. So at 11 kilometer, what is the layer? This layer is called as tropospause. And then yeah, in the stratosphere the temperature remains constant, and in the troposphere both the pressure and temperatures are varying, and this is what, okay, main thing we need to note down. And first let us mm, uh, develop the equation for finding the pressure and temperature in troposphere, and then we'll go to the stratosphere. So pressure and temperature in the troposphere, uh, just we can put it in this way. Equation as per International Standard Atmosphere. So the equations for finding the temperature in troposphere is nothing but T naught, means not T naught, T equal to T naught minus lambda H. Here this lambda is nothing but lapse rate. And T is the temperature at any particular temperature, that means particular height. So we can say this temperature up to 11 kilometer, okay, we can just use it. So this can be up to 11 kilometers. And this one T naught is the sea level temperature. And our H is the height that also varies up to 11 kilometers. And now we need to find out what are the variations in temperature, and also with respect to the temperature, how pressure is going to vary. For finding the pressure variation in troposphere, we have a standard equations. Means we are using the hydrostatic equation and also ideal gas equations, or perfect gas equations. So when we say this hydrostatic equation, for hydrostatic equation generally we used to say this is. So this is what we used to call it as hydrostatic equation, rho g dh. So for this is for vertically downward directions, because the rate of change of pressure in a vertically downward direction is equal to the weight density of the fluid at that point. So that is what hydrostatic law says. So when we say this is for downward, then because our standard atmosphere, okay, is in the vertically upward, above the ground. So we can just write it as this equation minus for rho g dh for our that upward direction, and that means for the height increasing from the ground level. So this is the hydrostatic law for increasing altitude from the ground level. And we can have our perfect gas equation, that is nothing but P is equal to rho RT. So we know. So let us see, this is first equation, and this is second equation. So by using these two equations, we need to work on just how to develop this one. So just let us divide equation 1 by 2. That means 1. If we divide by 2, then what will be there? So this will be like dP by P. So this is also equal to minus rho g dh divided by rho RT. So here what will happen, the rho will get cancelled out. So we will have a minus g dh divided by RT. So we are having dP by P equal to minus g dh RT. So this equation further we can develop. So that means dp by p equal to dp by p equal to minus g dh by rt. So here this temperature T is nothing but what we have seen already. T is nothing but T equal to T naught minus lambda h. So here we have a h. So our differentiation factor or integration factor will be h. So we have to substitute this one here, and therefore our dp by p equal to minus g by r dh divided by T naught minus lambda h. So this is equation we have to integrate. So let us integrate on both sides. If you integrate on both sides, okay, so with respect to that means lower limit and upper limit. Lower limit will be 0 because our pressure P naught, what is the pressure at sea level, and up to pressure at 11 kilometer we can see. And similarly here also we can say it is h will be 0 and h equal to 11 kilometer. So this will be the limit. Okay, within this limit we need to integrate. So first, okay, so if you just if you take that into account, and then our this equation further becomes dp by p equal to minus g by r, then dh by t naught minus lambda r. So okay, so lambda not lambda or lambda h. So this is what we have to integrate. So when we are integrating, so what will happen, the left hand side will become ln p equal to minus g by r. So this is on the left hand side we have to apply the limit, this is, and then here. So on the right hand side what will happen, this also will be like ln let us consider this as the T1, that means H1 we can say, not H1, we can just put it like this, because T1 by T2, just let us see. So not T1 by T2, so it is like T11, and this will be T0. So and this equation, okay, again when we are integrating, and this will have some this one minus lambda, that means minus lambda will be coming here and not here. Now let us integrate this equation with respect to the limits. So on the left hand side we have a dp by p, and on right hand side we have this. So when we are integrating on both sides, so we will have this. So left hand side becomes ln p on the right hand side g by r. This, if you will integrate, we will get ln T naught lambda h. Then further, okay, so this has to be differentiated with respect to the integrating factor, so that will come minus lambda. So this is what we are just getting, and then we need to put the limit. So the limit can be 0 to this up to 11, we can say. So this further we can modify minus g by lambda, or because lambda is a constant, so we can take it out. The minus minus will become plus. So that means this minus and this minus. So we have a left out term ln T naught minus lambda r. So this is whatever is there in the bracket is nothing but T. So let's see this one. So again this can be modified. So on the left hand side we have a ln T11 by T naught. On the right hand side we have G by lambda r into ln. So in the bracket, if you apply the limit, the bracketed term will become let's say T11 by T0. So that is the idea. And then or we can have this T11 as T2 and the ground level temperature, so that we can say as T1. So we can write it like this. Ln even on the pressure also we can say. That means pressure also we can say T2 by T1 that is equal to G by lambda or ln T2 by T1. So this is, so in the case of logarithmic function, this power can be that means this can be taken to the power. So again we can, this equation further can be simplified and we can write like this: T2 by T1 equal to T2 by T1 whole power G by lambda r. So this equation just we can have it. So even just on both sides ln is there, so we can cancel out and then remaining will come as it is. So because the ln will be there, so we can just leave it. So we just finally we are getting T2 by T1 equal to T2 by T1 whole power G by lambda. So this is the final equation we can say for troposphere. And here, okay, the important point is we need to note down how the T2 and the T1 and T2 by T1. So T2 is nothing but it is the temperature at any altitude, we can say within the troposphere. That means T0 minus lambda h, and this is nothing but we can say h any altitude, and T1 equal to T0 minus lambda h1. So the h1 is the sea level height, so 0 altitude, and this altitude okay up to 11 kilometer we can go. And similarly for the pressure. So this is the idea. So this is what about troposphere. So already we have seen how to find out the, that means temperature, and this is the equation for finding the pressure. And also we have the relationship between these two, that means pressure and the temperature. So now let us see what happened in the case of stratosphere. So in the case of stratosphere, as we said, the temperature remains constant. It means from 11 kilometer, what is the temperature? The 11 kilometer, generally we used to say the lambda h. This is the let us find out the temperature at 11 kilometer. So this will be the temperature, sea level temperature is nothing but 288.18 minus the lapse rate is nothing but 0.0065, and h is nothing but you can say 11,000. So if we do so, then this becomes 216.5 so Kelvin. So this is what temperature at 11 kilometer. This temperature will remain constant in stratosphere. So this will be the temperature up to 20 kilometers. So up to 20 kilometers, this temperature will remain constant. So you can just see up to 20 kilometers, because our stratosphere is up to 20 kilometers. So this will remain constant. And another thing is for every 1000 meter, the temperature decreases in the troposphere. In the troposphere, for every 1000 meter, 6.5 5 degrees Celsius. Because for that is the we have just left out that point. For every 1000 meter, there will be a 6.5 degrees Celsius decrease. So that is the idea. So this will be decreasing for every 1000 meters. So that is how finally we are ending up with a very low temperature at 11,000 meters. So that is we need to note down. And okay, now let's see in the stratosphere what happens. So we have seen about the temperature. Temperature remains constant in the stratosphere, and from 11 kilometer up to 20 kilometer, the temperature will remain constant. So that value we have seen 216.5 Kelvin. So then now what happened to the pressure? The pressure, we know the equation. So the same equation, hydrostatic equation and perfect gas equation we have to use. And this is G by R dH by this. So here what happened, our temperature remains constant. So here okay, so in dP by we can write like this. So our dP by P equal to minus G by RT into H. So then now we can integrate this one. Integrating on both sides. So what we will get? We will be getting this. So on the left hand side it becomes ln P, and the right hand side minus G by RT, because now the temperature is constant, so that is why we have taken out. So only it will become H. So we will have a limit. So 11 kilometer up to 20 kilometer. Similarly, here also we have a limit 11 kilometer up to 20 kilometer. So this is the formula for finding the pressure, and we have seen the temperature, so that remains constant. And so this, if you just apply the limit, what will happen? P20 divided by P11, so that will be equal to this. So when we take this into this one, then we will have a. So anyway, if you apply the limit, so it will become this. So minus G by RT, so H20. So if you take this, okay, H20 minus H11. So this is a formula for stratosphere. How to find out the pressure and the temperature. So these are the formulas for finding the pressure and temperature in troposphere and the stratosphere. And so we have some certain standard values. That means standard sea level values. So that value we can just see our standard sea level value T naught. T naught will be 101,325 Newton per meter square. This is roughly we can say 1 atmosphere. And then we have a temperature T naught equal to 288.18 Kelvin, and then density, so rho naught equal to 1.225 kg per meter cube. So these are the standard values we are using in the international standard atmosphere, and especially these values are okay at the sea level. So other values how to find out, we have seen the equations and we have seen the formulas.